Good afternoon.
Well, I gave you all my love and I gave you all my trust and I gave you everything that you need. But you only told me lies and
Hello.
made me realize that, babe, you ain't no good for me. I can't be with you, you can't be true. Now I know just what I got to do. Gotta hit the ground running just as fast as I can. Gotta hit the ground running.
Hello.
Just as fast as I can. Well, you're begging me to stay, but
All right, let's get started. So this week and this week we're going to talk about some interesting stuff that's going to be closely related to calculus. Assuming that you're taking it in the future, should be very useful. This course is called Precalculus, after all, right? So let's get to it. Well, first of all, let's look at number one. When your year starts, when you start working, apparently, because to fight inflation, right? So your salary should increase, theoretically, year over year. Now, here they say you start from 25,000. If your salary annually increased by 5%, how many years will it take you to earn a total of $1 million? Notice that they say a total of $1 million. They're not talking about annual salary being a million, right? So a total of $1 million. So that means you're gonna add them all up, right, throughout the years. Make sense? So this is year one, right? 225K, right? So what would the next year be? Year two. You're 5% more, so wouldn't that be what? 25,000 times 1.05? Does that make sense? And the next one would be 25,000 times 1.05 times 1.05 again, which is square. Now, normally we would just keep going, but here we're adding this, right? We're adding this together because they say sum, right? So add all the way until the end. I want this sum to be what? $1 million. $1 million. Okay? So, what kind of series is this? This series is sum, right? Is this geometric or arithmetic? What kind of series is this? Geometric. So remember geometric series, your sum is what? G1 or first term plus 1 minus r to the n over 1 minus r, right? This was a formula we talked about last week. Why is this crooked? This is very annoying. Let me turn it a little bit. One sec. Let me turn this leg a little bit. Hopefully it fixes. That fixes it. Okay. So, we're good? So, if that's the case, then we're going to use the formula here. So, in this case, R is going to be 1.05. Because the ratio in geometric is what you multiply by, it's not the actual rate, right? It's not 5%, okay? So it's 1.05. So G1, 25,000, times 1 minus R, which is 1.05 to the n power, over 1 minus 1.05, right, 1 minus R, should equal to $1 million. Okay? And then now you calculate. So to calculate this first, I would divide this over and multiply that over. Okay? So divide this, I'll get a 4 and then multiply. So it'll be, we need a calculator for this. So 1 million divided by 25,000. Oops. Right, divided by 25,000. That's 40 times, it's going to be 0.05. That's 2. Okay? So we want to know 2 is equal to, so these will be gone, so 1 minus 1.05 to the n power. So naturally, I do everything right. Oh, negative 2, sorry, negative 2. Because this is negative 0.05. Okay. And then you move that over, so negative 3 is equal to negative 1.05 to the n. Notice that this negative is after, so you can take them out at the same time. Okay. So then n, you remember how to solve for this? If I want an exponent, how do I solve for an exponent how do I solve for this? What is the method we use? Log both sides, very good. So then log, you can use any log, okay? I can use common log, you can use natural log, you can use log base anything. Why do we do that? Because log properties, I can pull this down, right? So here we go. Log 3 equals n log 1.05, and you can divide this over, so n is log 3 over log 1.05, which is approximately 22.5 or about 23 years. Okay, years. So overall gross income will be $1 million cumulative, right? After you add them all up, in 23 years with that salary increase and that base salary, you will get $1 million overall. Okay, but that, I mean, obviously doesn't mean that you save up 1 million. It basically means that you have earned 1 million overall. Okay, makes sense. All right, so today we're going to talk about before we talk about series, let's go back to sequence real quick. So what is this? 1/2 to the n power. Okay, so 1/2 to the n power, this is a geometric, right? Or we call this an exponential function. What happens if you increase your n? So for example, this to the 1 power is 1/2. To the 10 power, it will become, if you put it in your calculator, so put 1/2, oops, 1/2 to the 10th power, gives you this. What is this? Scientific notation, your favorite, right? This is a 9.76 times 10 to the -4, okay? And you can do it for 100, right? Oops, 100 power, then it's 7.88 times 10 to the -31, which is a very small number. And you do it again to, they want 1,000, right? Oops. They want 1,000. Whoa. Hey. Apparently, if you keep multiplying by 1/2, it'll be 0. Does that make sense? Is this true? You can actually get 0 from multiplying by 1/2 after 1,000 times? According to calculator, it's true, but how come the calculator does this? The answer should be no, right? You should have something left, although it's very small. This is called the calculator gave up. I mean, not gave up, but yeah, gave up. All right, but you shouldn't. Okay, so this is because, why did I say give up? It ran out of places, okay? Basically, they didn't have enough places to hold these numbers, so they ran out of places, okay? If you look at the graph that we had before for exponential decay, if you remember, you just graph a few points, you'll remember. So at 0, it's 1, because, you know, 1 at 0 is 1. And then 1 is half, and then it keeps reducing by half, 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 half. Eventually, you should get an exponential decay. I'll put it here. By 0, 1, 1 half, 2 is 1/4, right? 3 is 1/8, and it keeps going. Okay, like that. And the graph should look like this. Now, interesting thing is that this line doesn't actually exist because your n is in whole numbers, right? So you should just graph points. I'm just showing you the trend line, but it should approach 0, but it's not actually going to 0 at any given number. Okay? Now, moving down. So introducing new notation. I don't know why it says x, but it should be n instead. Over here. Here it says x going to infinity, which actually should be n goes to infinity. I don't know why it says x. Maybe it's just a notation. It doesn't have an n, but it's supposed to be n. These two should match. Okay. So because look at this. Look at this. This is going to 0, right? So we say this is 0. Now, how do I read this? This reads. This reads. The limit of 1/2 to the n power as n approaches to infinity is 0. Okay? That's how you read it. No, when you see LIM is limit, and what is the limit doing at when n is approaching to infinity, not at infinity because infinity is not a number, when it's approaching to that very, very big number, what will happen to my expression? In this case, the expression when n goes big becomes small because you're 1/2, you keep halving yourself, right? And eventually, one day, in the near future, it should approach to 0. Although that future is never coming. Okay? Basically it. Okay? So the limit of n approaching to infinity for the function 1/2 to the n power is equal to 0. Nice, Kevin. Nice. Oh man. All right, we're okay with this. Let's go to the next page. Okay, next page. So Now let's look at the graph of f of x equals negative half x plus 2. Okay? So if you look at this, so remember how to graph this? Don't say you don't know how to graph a line, okay? Get out of here. So when you graph this, right? Plus 2, so 1, 2, right? Negative 1/2, right? So you should go to 4. Oops, 4. This is 5. 1, 2, 3, 4, right? And then you should use a ruler, right? Where's my ruler? I don't know where my ruler is. I use a credit card. Should censor this. Actually, I shouldn't use a credit card. Bad idea. I don't know what people do on YouTube. Maybe I'll get scammed. Here, I'll use a gift card. So, here we go. Here's the line. Okay? So, what happens if x goes to 5? So where's 5? X equals 5 is here, right? Right here. So when x goes to 5, now when you're approaching 5, there's obviously two directions to do that because 5 has both sides. Unlike infinity, infinity only has one side, right? Because you can only go that way to go to like to the right to go to more infinity. But going towards a point can come from two sides, right? You can come from the left side and you can come from the right side. And in fact, we're going to look at it from both sides, okay? So where does this wants to be when I'm going limit as x approaches to 5, okay? But I'm pointing from the left side, so left hand. This is called left hand limit. I put 5 minus, okay? This means I am from the left side, okay? And of this function, so I'm going to put the function negative 1/2 x plus 2. What does this equal to? Well, what does it want to be at 5? Well, if you look at this, the function wants to be basically at f of 5, right? Because it doesn't have anywhere else to go. So it wants to be negative 0.5, I think. Because if you plug in 5, you'll get negative 0.5. Usually you can just plug it in. Okay, sometimes you can't. From the right, limit as x goes to 5 plus, which means from the right side, when x is slightly bigger than 5, then this will be same thing, negative 0.5. Hey, you see how they agree with each other? They're the same, right? So we know limit x goes to 5 of this is negative 0.5. Now, in order for this to work, both sides have to agree. If both sides don't agree, there's no limit. Okay? No limit, meaning that there's no value it approaches to. Okay? A little bit interesting. All right? Now, what happens to this function when x goes to very infinity? Well, when this keeps going, what happens? No way return, right? You just keep going down. So, negative infinity. Okay? negative infinity. There's no coming back, right? You just keep going down. No, nothing it's approaching to. You just keep going down. Okay. How are we doing so far? Does this make sense? Comfort level 1 to 10. Give me something. Give me a number. Type. 8 and 9 is not bad. Not bad at all. 7's not bad. 7, 8. 7. Okay. Let's continue then. The next part, we're going to look at a different function called the, we call this rational function. This is 1 over x. So let's look at the graph first. When it's 1, it's 1 over 1, right? We're going to graph this. Okay, well, I'm going to graph in the middle because I'm going to use it for both sides. Because 1 is x goes to 0, 1 is x goes to infinity, right? So I'm going to graph this. Okay. So when x is 1, what is my y? Y is 1, right? 1, 1. When x is half, then y is 2, right? Because 1 divided by half. 4, 10. It's just reciprocal because okay. You're just taking 1 over, right? So that's going to be flipped back, and this will be 1,000, right? So what does that tell you? It tells me the more I'm approaching to 0 from 1, so 1 is 1, right? And then when it's half is 2. Right, 2 is here. When it's half is 2. And then the next one is 4, so it gets closer. Okay? But it can never be 0, right? It just keeps going higher. So it will go to super high after you go super small. Because this is a very small number, right? This is going to 0. And what will happen to f? It goes to infinity. Now, notice that which side am I coming from? I'm approaching it from the... right? I'm approaching to the right side of 0, right? This is 0, right? 0. But I'm approaching from the right side of 0. So it's 0 plus, okay? 0 plus. Now, notice that here they already say x is greater than 0. So you graph that part, okay? Now, on the right side, as you increase your value, like 100, then obviously you get smaller, right? 1,000, and then, 1 over 100,000. Wait, this is 1 million. Sorry, 1 million. So, as you increase, obviously, 1/2, 1/3, all the way down. So it should, as you go higher, infinity, this should go to 0. Now notice here I didn't say it's equal to 0 plus, because in y value, you don't control where it's approaching to. You just say the limit is going to that point, right? So this is just something different, okay? You don't say it's going to 0 plus. You just say it's going to 0, okay? Now, however, if you want to find the value of this is obviously 0. Okay, infinity will be 0. But this, if its limit as x goes to 0 plus, that's going to be of 1 over x, that's going to be 0. Sorry, that's going to be positive infinity. Okay? Because we just showed here, right? But what happens to the left side? Limit as x goes to 0 minus is equal to what? Well, technically, I'm not defined in the domain here, but I just want you to know that if you're doing this, right, if you draw the left side, it will look like this, okay? It will look like this. So technically, at 0, these two don't agree, so you'll get a no limit. No limit at x equals 0, okay? Or, yeah, so if you say the limit doesn't agree with each other, okay? But, so you can say this does not exist in the normal circumstances, in all real numbers, okay? But in this context, since they already restrict x greater than 0, we know that this is actually 0 plus instead of 0. Okay, you're shooting from the right side, so it's going to infinity. Okay. All right. Quickly review. This is a rational function where it has a vertical asymptote. Vertical asymptote is there because you can't divide by 0. And when you come from the right side and the left side, the result is drastically different. By drastically, I mean infinitely different, right? You go here from the right, you go to positive infinity. You go from the left, you go negative infinity. Okay? So in this case, since we're only looking at the right side, the going to 0 actually means going to 0 plus, since they already defined that part for you. But, you know, normally we call this does not exist. Okay? All right. Now, let's look at some more interesting functions, rational functions. So look at this. So when it approaches to a value, a limit, finite limit, L, then we call this a convergent or converges to L. Okay? Now, if it doesn't have a limit, like infinity is not a limit, it's like it's an infinity, right? There's no limit to infinity, so it's not a limit, okay? Or if it's oscillating, we also call this divergent, okay? Converge means it goes to a point, right? You converge to a point. Diverge means you don't converge to a point, okay? Simply like that. What does it mean by oscillating? It means that, for example, remember y equals sine x? Right, what does that look like? That look like up, down, up, down, up. Does this thing ever converge to a point? Like, does the value converge to a point? Doesn't it just go up, down forever and ever? That's called oscillating. Okay? This one's called oscillating, so this has no limit. As x approaches infinity. Okay? Does that make sense? You have to converge to a point in order for this to work. Let's look at these parts. So this one, 2n minus 6 over n plus 10. Okay? So when we are approaching this kind of problem, approaching to this kind of problem, all right, approaching infinity, you want to look at what we call, once again, the end behavior of these things. To look at these, we have to look at how these values change. By the way, this is n, okay? So to analyze this, we understand that 1 over n as limit as 1 over n as n goes to infinity is 0, right? We just talked about this. As n goes to infinity, 1 over n is 0. Okay? So we want to use that fact. Okay, so to do that, I used a method called divide. Okay? Divide by n, top and bottom. Okay? So if I divide by n, I'll get 2. I'll slow down a little bit. Okay? Here we go. 2n minus 6 over n plus 10, right? I'm going to divide everything by n. That's a valid move, right? Because you're just multiplying by 1. If you do that, the next level... Oh, by the way, do not drop your limit. Okay, don't drop your limit until you get the answer. Okay, so I keep the limit. Let's see. Let me move this slightly more upright. Okay, so this becomes what? 2 minus 6 over n. This is 1 plus 10 over n, right? Now, what do these things equal to? 6 over n, 10 over n. As n goes really, really large, what happens to these? What do they become? Type. Almost 0, close to 0, which should just go to 0, right? So if there's 0, then what do I have left? 2 over 1, which is 2, right? So that should be my answer. Let's see if it makes sense, okay? Now, if you look at this in a conceptual way, 6 and 10 in the long run doesn't change. They stay the same. So when n is really large, like 10 million, so you get 20 million here, and you get 10 million here. The minus 6 and 10 is negligible, right? You don't even have to think about it because it's so small compared to the rest of it. Let alone infinity is much larger than 10 million, right? So overall, the value should approach to 2. Does that make sense? Next one. So same method I'm going to use. I'm going to divide by, in this case, so I want to divide by the largest value. Okay, usually that's what I like to do. So I'm going to do n squared. Okay. Some people like to do n and then just do that afterwards. I usually do the largest power. So I just get 29n over n squared plus 10 to the 5th over n squared, 5n squared over n squared minus 8 over n squared. All that. Then what happens? Well, simplifying it, I'll get 29 over n. This thing doesn't change. This becomes 5. This is 8 over n squared. Okay. See all these zeros I'm seeing? 10 to the 5th is constant. Okay, it's big constant. It's still constant. This all goes to 0, right? So overall, what do I have left? 0 over 5, which is still 0. Okay. Let's look at conceptual. 29n plus 10, what kind of function is that? What kind of function is 29n plus 10 to the 5th? 29n plus 10 to the 5th. What is this kind of function? What type of function? You can do constant, quadratic, linear, cubic, quartic. What kind of this function is this? Linear, right? What kind of function is the bottom denominator? The bottom of quadratic. Which one grows faster? Well, quadratic grows faster than linear, right? Since that's the case, the bottom part outgrows the top eventually, and the top becomes too small for the bottom, then therefore it will approach to 0 because you're dividing by too large of a number. Okay? And eventually it will be 0. Alright? how we're doing. Does this make sense? Give me 1 to 5. Oh, sorry, 1 to 10. 1 to 10. I don't know why I said 1 to 5. Watch me get a bunch of 4s. 1 to 10. Oh, nice. All of your 3s and 4s are out. Alright. So, looks like we're like 6 to 9. Something like that, right? So, we'll get more to it. This takes a little practice. Okay, you have to kind of use some imagination as well, because this is not a how do we put it? It's new, right? Kind of new, kind of. It's very similar to end behavior. This is what end behavior of the graph came from. Okay. All right. So let's look at some practice problem on the left side. All right. So next page. All right. So now let's mix up different functions to see where this goes. Okay. So when sine n, like I said, what does sine n look like? It goes between -1 and 1, right? It goes between -1 and 1. Okay? No more, no less. Oh, well, it's between -1 and 1, right? It's oscillating. What about this? This keeps increasing, right? This goes to infinity, right? So it looks like that. So, naturally, when you put them together, what would the overall value go to? You're essentially bounded between, all right, think about it like this, okay? Think about it like this. So, sine is between what? -1 and 1, right? You agree? Sine is between -1 and 1. So, naturally, the limit, all right, should be in between as well. So n goes infinity, n goes infinity, n goes infinity, like that. We're not interested in just sine though. What are we interested? Because normally, if you look at this, limit of -1 is just -1. Limit of 1 is just 1. Limit of sine does not exist. But if you put it over n, like how we have it in the problem, right? Sine n over n. Then when you look at this, okay, when you look at this part, right, approaches 0. This part approaches to 0. Where's this going? Has to be 0. Okay? We call this, in calculus, we have this famous theorem for this. It's called the sandwich theorem. Spitting out a little extra stuff for you guys today. This is called the sandwich theorem, or squeeze theorem, as some books have it. Basically means left goes to one side, right goes to one side. Of course, the middle one has to go to that side. Okay. So it has to go to 0, right? Answer is 0. If you look at the graph of sine n over n, it will also make sense because it kind of looks like this. It oscillates until 0. Okay. But does it count as a limit if it? Yeah, it does. So it doesn't matter if it crosses multiple points. Horizontal asymptotes can have the graph crossing because it doesn't affect the fact that it will be a 0 or not, right? Sorry, it will be a function or not, because this will be a function no matter how many times it oscillates through the 0 line. So it does count. Yes. Okay. Does that answer your question? Push it slightly this way a little bit. Okay. Look at e to the -1/2 to the n. Well, we don't like negative power in general. So I like to remind you, what does negative mean? What does negative power mean? What does that do? What does this exponent negative does? What does it do? One over, right? So it'd be 1 over whatever you had, right? E to the 1/2 n. Well, when n goes to infinity, this is an exponential function. This goes to infinity, so you get 1 over something goes to infinity should equal to 0. Okay. Once you graph the graph, you will realize that the whole graph is an exponential decay anyway, so it should go to 0. Okay. All right, number 3, 1.001 to the n power. Does this go bigger or smaller as n goes to infinity? Think. N goes to infinity, 1.001 to the n power. Does that go higher or lower? Has to go higher, right? Has to go higher. This is the same thing you use to calculate your overall principal value. Your value in the bank, right? Didn't we do like 25,000 times 1.00 something to the n power to get more money, right? So this should be higher, so eventually it will go to infinity, okay? And there's no bound to this, right? Exponential growth. Exponential growth goes like that, okay? Exponential growth. All right, next one, number 4. Number 4 looks like another one that we will divide by n squared for. So we're gonna do that. Okay, divide by n squared. So once you do that, you will get. So I'll directly simplify. Okay, I'll simplify into this. So after you simplify, it looks like this. This is 0. This goes 0. Now you're left with -1 to the n power over 1. Now, what does this look like? As n goes bigger, right? Doesn't it be, remember n is a discrete number. It's a whole number, right? It goes infinity. Then what would you get? You get a -1 to start, then 1, then -1, then 1, then -1, then 1, then -1, right? So, does it get bigger? Does it get smaller? What does it do? What is it doing? Right, because these don't matter. All that matters is this part. So, it's -1, 1, -1, 1, -1, 1. What is this? Does it approach to one number? Does it converge to one number? Okay, limit has to converge to one number. Does it converge to one number? So it's two numbers, right? -1, 1, -1, 1, -1, 1. So, limit does not exist. Up, down, up, down, up, down, up, down, right? So limit does not exist. We call this the oscillating divergence. Okay? Compare this to number 1. Right? Number 1 also oscillate, but it oscillates slow. The oscillation keeps getting smaller and smaller. Eventually, the oscillation will be 0, right? Because you're going up, down, and it's tighter and tighter. Which as this one, you don't, right? You just go up, down, up, down, up, down, up, down forever. Okay, so we call this divergent. All right, I'll give you some time, like 1 minute to try number 5. And if you got number 5, you can try number 6. 6 is very interesting. So, if you're here, please type you're here so that I can take attendance for the formality of it. I do understand today is isn't it a physics test today? AP Physics? Right. So, but people who are taking AP Physics already has their attendance done, so I don't have to worry about them. But if you're here, please say you're here. I know people who are taking the... Whoa, Nathan, you're already back? 40... Oh yeah, it's only 45 minutes, huh? So it should be just over by now, right? I don't think I'm missing anybody. Now everyone seems to be here. Are you like taking an AP test and watching stream at the same time? Who is this? Who are you? Who is this guy? Gotta state your true name to be welcome to the group. Look at this. Yeah, I mean, I kind of figured it's Ch.12 because the way the screen name goes, the way the font is used, you know, like I can almost picture his handwriting in that. Regardless, we figured out what number 5 is yet? We're almost done. So number 5, you divide by n to the 5th, right? N to the 5th. So you're going to divide by n to the 5th, highest power, okay? So it's 10 to the 9th over n to the 4th. The bottom part is 1 minus 2 over m to the 5th. Right? So all these go to 0. So you get 0 over 1, which is 0. Okay? You want to divide by the highest power so that it gives you a bunch of over n's. Okay, over n square, over n cube, all that stuff. Okay. All right. Number 6. Isn't number 6 interesting? There are 2 ways to do this. 1, you can actually graph this. 2, let me remind you. So how do I, because log is very exponent friendly, but it's not radical friendly, right? So we're going to change that. Not irrational equations, Kevin. So Kevin asked, is there a case where the denominator variable has the highest power, but the limit isn't 0? Not if both of them are polynomials. So like, not even polynomials, like power functions. So like, if your bottom part is higher power, usually means that you have higher growth rate, which means it goes to 0, right? Unless you have a mix of different equations. For example, the bottom part is n to the 10th, right? And top is exponential e to the n, then it will go to infinity because e to the n is way higher. right? But in the case where both of them, are polynomials or power functions only, then this will always dominate, right? But if you have something like e to the n over n to the 10th power, this is more powerful than this, so this will go to infinity. Okay, limit as n go to infinity, that goes to infinity. But if this is the same type of function, then the higher power will win. Okay, we'll go to 0. Does that answer your question? Right. With the same type, the power obviously dominates the whole thing. Okay. All right. So log is exponent friendly. So remember what n through can be written as a power. Isn't that what? So if its square root is 1/2, cube root is 1/3, n through needs to be 1 over n, right? Yeah. Then obviously you can move this down. So this will then be, right, use the fact. So what is log 10? Anybody remember what log 10 is? This is 1, right? I mean, regardless if it's log 10 or log whatever, this is just a number, right? So overall, this goes 0, right? So 0 times something, that's 0, right? 0 times a constant. So overall is 0. Okay. All right. Number 7. So this one you kind of have to go layer by layer, right? Because this one kind of has 3 layers, right? 1 over n, cosine, and then log. So to do that, we basically go layer by layer. So we're gonna go, so we can put this limit all the way inside. Okay. So this we already know is 0. What's cosine 0? What's cosine 0? Trig values. Oops. Little bit of packet lost, but cosine 0 is 1, right? So overall is log 1. What is log 1? 0. The log is relevant, so you have to take the log afterwards, right? So basically a rule that you can keep in mind is that limit as x goes to infinity of, let's just say, f of g of x, something like that, right? That's a composite, right? I feel like that's too many, that's something like that, is equal to f of limit as x goes to infinity of g of x. Okay? Like that. Okay. Okay. So, the last part is looking at different functions again. A, n goes to a point, right? So the last part is going to a point. N goes to the point 2. Now this is remember, when we can plug in 2 to the function, we can just plug in 2. So this is what? 2 squared minus 1. The answer is 3. Oh, how come I can just plug in a number? Because there's no break. We call these continuous functions. Okay, continuous. All right, if you look at the graph, what does that look like? It looks like this, right? This is a graph. What happens at 2? Well, at 2, from left and right should go to the same point because it doesn't break. I know, this fails. It's supposed to be x. You know, I don't know what's wrong with this packet. Like, when it's supposed to be n, it gives x. When it's supposed to be x, it gives n. I don't know why this does this to me. Okay? Yeah. All right. Number 9. So, number 9 is interesting. Let's leave it for last. Number 10 we talked about, right? Number 10, A, B, and C. Remember what the answer is? Remember we looked at the graph? It looks like this, right? What happens when it goes to the right, from the right-hand limit? Infinity, right? The left-hand limit, negative infinity. Both sides don't agree, so we say this does not exist. DNE. DNE is actually a real thing, right? So you can put DNE for anything really. For limits. If it does not exist, you can put the DNE. Because we put it a lot in calculus, so you can learn it. Okay. Are we okay with number 10? So we can talk about number 9. Number 9 is very interesting. Good with number 10? Alright. Number 9. Can you plug in 0 on this one? If you plug in 0, you get sine 0, 0. This is 0 as well. 0 over 0 is undefined, obviously. Right, so you can't just plug in 0. So let's look at the graph first. Okay, let's look at the graph. Sine n over n, right? Oops. So the graph looks like this. Okay? So right, and this part is 1. So what do you think at 0 it wants to be when it approaches to 0 from left and right? If you just look at the graph looks like this. Doesn't it want to be 1? It wants to be 1, right? Does that mean 0 over 0 is 1? No. But, a good point. Doesn't sine graph start at 0? Well, it does, but we're not talking about sine, right? We're talking about sine n over n, right? This is the beauty of infinity. You know, when it comes to infinity, not everything you think it's gonna be will be. Okay? Now, there is a geometric proof for this. The official proof is in geometric proof. Look it up online, okay? Has to do with geometric proof for this, combined with sandwich theorem. Okay, so this is the original limit proof. There's another proof, another method in calculus we use. I'll update you. If you're interested in this, you can look it up. It's called the hospital rule or L'Hopital's rule. Later on in calculus you'll use to solve for this. But the normal proof is this. Obviously you can look at the graph and see that it wants to go to 1, okay? But this is a special case that later on we sometimes just accept as fact. Okay? All right. So your homework is already on Google Classroom, okay? Please do your homework, okay? I can't emphasize enough. Google Classroom, there's 2 worksheets. It's basically all limits. It's basically the next 2 pages. You don't have to print it out again because it's the next 2 pages of your packet, okay? So it's this one and the page after. All right, these 2 pages will be your homework. So if you have that printed out, you don't have to reprint anything. You can just do them. Okay? Any other questions you have before I let you go? Today's lesson is extra long, just over an hour, right? But there's a lot of information to swallow and digest. So take your time. And our time together is numbered, right? I mean, numbered is limited. I got it. The time we have together is limited. So should cherish every moment together. Who knows? We're gonna see. Who knows what's gonna happen? All right. Anything else before we close? Gotta get out before the lags start coming again. One over x had more of a limit than a linear equation because they are technically can't meet the x equals 0 point. I think you're mixing up the 2 concepts. So having a limit, meaning that your limit has to be when x is going to a certain value, okay? So it's not necessarily having a limit or not in general. It's more like, what does my function wants to be when my n value or x value is approaching to another point? So when that approaches 0, then this function wants to be at 1, so the limit is 1. Okay? So if you're looking at like what happens if you have had limit at 0, then the linear equation will always have a limit at 0 because it's continuous. Right? So if you have a straight line, right? So the limit, for example, at x plus 1 at 0 is 1, right? Because it wants to be 1. But limit as x goes 0 of 1 over x is undefined or doesn't exist. Okay? So nothing can equal to infinity because infinity is not a number, it's a concept, right? So you can approach infinity, but the limit can equal to infinity because that's what limit means. You're approaching to infinity. Okay? So there's no such thing as more of a limit because we're not using limit as bounds. Okay? What you're using limit at in terms of your terminology seems like you're using limit and bounds interchangeably, but bounds are bounds, right? Like sine, right, has an upper bound and lower bound. These are bounds, but the limit is not a bound. Okay, in English they are interchangeable, but in math they're not. that makes sense. Now, limit is a value that a function wants to approach to, and bound is a maximum, a value that it's contained by. Okay. All right. Any other questions? If you have any, you can stay. If not, you're free to go. Have a good week. Remember to do your homework, okay? Goodbye. What is this drum beat? Goodbye. Bye.